Hi everybody, today we are going to talk about counting principles. So we're going to start with the most basic counting principle, which is the fundamental counting principle. So this is assuming that maybe there are two events, we can call them E sub 1 and E sub 2. If event 1 can occur in M sub 1 different ways, event 2 can occur in M sub 2 different ways, to find the number of ways that the two events can occur is just by multiplying the number of ways each of them can occur by each other. Now, of course, this would work for more than two events, and I really just hope that you don't overthink these types of problems. You're pretty much just looking at each individual thing and saying, how many different options do I have from this? How many different options do I have for this? And then multiplying those all together. For example, if we want to find how many different pairs of letters from the English alphabet are possible, well, we're trying to fill two spots because we have a pair of numbers. So for that first number, there's 26 options. There's 26 different ways that I can pick a first number. And for that second number, well, I have 26 numbers again. There's nothing in this problem that suggests that numbers can't be repeated, so you just multiply the number of options for each slot, and we get 676. Let's go ahead and pause the video and give this problem a try. So here there are three numbers that we're picking, and each of those numbers, there's 30 different options. So we just do 30 times 30 times 30, and it is 27,000. Now let's try one where there is a little bit more thinking involved. So it says, how many different telephone numbers are possible for each zip code? So we know that the zip code is the first three, but within each zip code, you can have a local number which should have 7 numbers. So the local number, it can be any numbers for each slot, except we do have one restriction. You cannot begin with a 0 or 1, which means this first number is a little bit more limited. Now for all of the other numbers, we have 10 options for each one, 0 through 9. So those each have 10 different ways or numbers that we could pick. But for that first one, we have to take away 2 of those options. It can't begin with a 0 or a 1. So we actually only have 8 options here. And then I just multiply all those together and we get 8 million. All right, go ahead and pause the video and give this one a try. And I know that says that it's a product number, but it starts with a letter. So think of it more as like a product code. Okay, so this product code or product number has 5 or 6 different slots to fill. The first one is the letter, and then it's 5 numbers. So there's 26 different things I can pick from for this first space, and then the remaining 5 have 10 different things to pick from because those are the numbers. So that gives us 2,600,000 different ways I can make different product numbers. Okay, so now we're going to talk about what are called permutations. So permutations is when you're ordering elements in a way where the relative position matters. So it matters which thing comes first and which thing comes second and which thing comes third, so on and so forth. So if you just have n elements and you want to find how many different ways you can order them, all n of them, you're using every single element, the formula for that is just n factorial. And you guys will see we actually don't really need a formula for this. We can just use our basic counting principles, but technically the formula is n factorial. Now, if we have n elements and we care about the order that we place them in, but we don't want to use all n. Let's say we only want to use r of them. So like, let's say we have 10 racers, but I only want the top 3. There's a formula for this as well. So it's n pick r, and it's just n factorial over n minus r factorial. So this type of scenario, once again, as well, we can kind of use our more basic counting principles, and we can end up with the same answer, but there is technically a formula for it. So let's give this first one a try. This one says, how many permutations of the following letters are possible? So here we want to use all 6 of these letters, and we want to know how many different ways can we arrange them where the order matters. So we can do this with our basic counting principles. So there's 6 slots. And this one, you have to make some adjustments. So since we're placing each one in a specific spot, for this first space, I have 6 things to pick from. So there's 6 possible outcomes there. But for the second slot, I've already picked one of the letters and has already gone somewhere. So our second slot actually only has 5 things to pick from, and then 4, and then 3, and then 2, and by the last space, we only have 1 thing to pick from. So you might notice that this is just 6 factorial. So remember, the formula is just n factorial. There are n terms, so that's kind of how that formula works. So whether you use a basic counting principle or you actually just use the formula, you should get 720 different ways. All right, now let's try one where we are not using all of the elements. So here we have 8 horses that are running in a race, and how many different ways can these horses come in first, second, or third? So here we can certainly see that this is a permutation because the order matters. Getting second place is very different than getting first place. So here, let's try this first with counting principles, and then we can try it with our formula. We have 3 spaces to fill. Those are the top 3: first place, second place, and third place. So to fill first place, we will have 8 different options. There's 8 different horses that might get first place. But once one of them has gotten first place, well, now there's only 7 different horses that might get second place. And since we've already filled 2 of the spaces, we only have 6 different choices for that third place spot. So here we do get 336. Now, like I said, we can also use that and pick our formula. So our n value is 8, and we want to pick 3. So we can use the formula n factorial over n minus r factorial. So you can see that this is just 8 factorial over 5 factorial. So everything 5 and below cancels out, and it's just 8 times 7 times 6. So we get that same thing that we saw up here. So either way is completely acceptable. And this, like I said, you do just need to realize that it is working because the specific order that we are placing the horses in matters, meaning it is a permutation. All right, go ahead and pause the video and give this one a try real quick. Okay, so here I use the formula. It's just 5 pick 2. So 5 factorial over 3 factorial. So there's 20 different ways that we can pick a president and a vice president. All right, so now we're going to talk about what are called distinguishable permutations. So this is something that we can do when one of the types of elements in our group has repetition. So let's say we're rearranging letters, but there's 3 A's in your group. So we know that if we just use a normal permutation, it just looks at where you're arranging each element. But we want distinguishable permutations, which means that there's no repeat in words that look exactly the same. So we can do this with this formula. So n is the total number of elements, n sub 1 is the number of one type of element, n sub 2 is the number of another type of element, and so you pretty much list how many of each type of element you have. You take the factorials of those and you multiply them together, and that becomes your denominator. So let's look at this example. How many different distinguishable ways can the letters in the word banana be written? So distinguishable means, so let's say I were to switch this A and this A. Technically, I did swap them, and it is a different permutation. However, when I swap those two, it looks exactly the same. It's not distinguishable. It's not unique. So we're eliminating that double counting for technically things that are different permutations, but permutations that look exactly the same. So if we swap 2 A's, we don't want it to be counted again because we end up with a word that looks exactly the same. So I always like to start by saying, okay, how many total elements do I have? So I can see here that I have 6 elements. Now I'm going to list out how many of each type of element. So I can see here that I have 1 B, I have 3 A's, and I have 2 N's. And this is a good thing to do because you can check to make sure that every element has been accounted for. 2 plus 3 plus 1 is 6. So now I can just use the formula. So it'll be 6 factorial over 1 factorial times 3 factorial times 2 factorial. and then we can just simplify from there. So I know it doesn't technically look like it really matters that we have that 1 factorial there, and it doesn't affect our answer, but it's still good to note that we still need to count how many of that type of element there are, even if it's just 1. And if you simplify this, there are 60 different ways. So once again, this is taking out the times when technically we've maybe swapped the N's or we've swapped the A's, but they end up looking exactly the same. So it takes out those things that have been essentially double counted. All right, go ahead and pause the video to see how many different distinguishable ways the letters in mitosis can be written. All right, go ahead and check your work. Here's the total elements, here's the number of each type of element, and I just plugged it into my formula. Here I did leave out the 1 factorials, and you should get 260. Okay, so now that we've talked about different types of permutations where the order matters, now let's talk about what if we're picking elements in a way where the order does not matter, and this is called a combination. Now just a quick thing to help you remember which one is which between combination and permutation. If you think of your combination lock, we know that you have to put the numbers in the right order. So I always say, combination locks are actually permutation locks because a combination lock, the order matters. So maybe that can help you remember. But a combination is just picking elements where the order does not matter. So the formula to find the number of combinations of n elements taken r at a time looks almost the same as the permutation formula, except we have this additional r factorial in our denominator. And this will take out pretty much all of the repeats that you get when you're doing permutations, because now they don't care what order it's written in. As long as it's the same 3 or 5 elements, it's only counted once. So this says, in how many different ways can 3 letters be chosen from A, B, C, D? So here, if this were a permutation, we would actually get a bigger number than if we are doing a combination. But here, there's nothing that implies that the order in which we pick these letters matters. We're just picking 3 letters. So that's how I know that it's a combination. So there's 5 to pick from, and we're going to choose 3. So we do 5 factorial over 5 minus 3 factorial times 3 factorial. So the 3 factorial on the bottom cancels out everything 3 down on the top. So we have 5 times 4, and then we have 2 times 1 here, and then we can simplify, and we end up with 10 ways. So this is essentially saying that ABC is the same as BAC is the same as CAB. It's those same 3 letters. It doesn't matter what order you list them in. Okay, let's try another one together. This one says a standard poker hand consists of 5 cards dealt from a deck of 52. How many different hands are possible? So here it's really important to understand that when you're dealt those 5 cards, it doesn't matter what order they're dealt in. The 5 cards in your hand, you can rearrange them in your hand and you can do whatever you want with them. There's no meaning or there's no value to getting one before the other. So that's how I know it's a combination. It's just the 5 cards in your hand. So this is going to be 52, choose 5. And this is when it is nice to have this formula with the bigger numbers. So we have 52 factorial over 52 minus 5 factorial times 5 factorial. And if you simplify this, you should get 2,598,960 different hands. So that's a lot of different hands. Okay, the last problem that we're going to do together, here we're imagining that we are a swim coach and we're forming a 12-member team from 10 girls and 15 boys that try out. Our team, we can only keep 5 girls and 7 boys. How many different teams are possible? So here we actually have 2 separate combinations going on. We have all of the different combinations of girls that we could pick, and then we're going to multiply that by all the different combinations of boys that we're going to pick. And once again, we know this is combination because it doesn't matter when you're picking a team, it doesn't matter who you pick first, second, third, fourth, or fifth. All of those members are on the same team, so the order doesn't matter. So if we want to find the combinations for girls, well, there's 10 girls that try out, and we can only choose 5 of them. If we want to find the number of combinations for boys, there's 15 boys that try out, and we can only choose 7. So this will give us 10 factorial over 5 factorial times 5 factorial. The first one's n minus r, then r. And then this we have 15 factorial over 8 factorial, 15 minus 7, times 7 factorial. So the number of combinations for girls is 252. The number of different combinations for boys is 6,435. And you multiply those two values together, and you get 1,621,620. Okay, last problem. Go ahead and pause the video and give this one a try. Okay, so here we want to figure out the number of combinations for women and then the number of combinations for men. So we find them separately and multiply those two values together, and then you should end up with 99,792. All right, that is all for today. Thank you so much for watching.